Welcome everyone to this first digital live stream of Forza Hydrogen Electric Racing. Whether you're new to the channel or you've been following Forza for a while already, it doesn't matter. Thank you for joining in. My name is Jesper Freins and I'm the current team manager at Forze. But I'll also be your host in these live streams. This is the first live stream of 4. So be sure that if you have any questions, you can put them in the chat and we'll make sure to answer them for you. Now, Forze is a team that has been founded 13 years ago. We started with hydrogen electric race cars or go-karts, I should say. And we moved all the way up to our current full-size race car that actually last August competed and got a podium place against conventional race cars, like race cars that race on petrol internal combustion engines. Now, in August, we started the development of our next hydrogen electric race car, the Forza 9. And to refresh your memory, about the setup of our digital design presentation spread over these coming 4 months. We are taking you through the major features of our new hydrogen electric race car, the Forza 9, once again. Enjoy.
So, how do you design a GT performance hydrogen electric race car? Well, we'll take you through the challenges. We'll need to go faster, which means more power, more hydrogen, more cooling, and a way to transfer the power into speed in order to cross the finish line first. In the upcoming months, we'll take you through these design challenges. Every first of the month, we'll reveal a new feature of the Forza 9, and during the live stream on the following Wednesday, we'll discuss the monthly challenge, our solutions, and your questions. So that in the end, the car won't look like this. Not the best design, right?
So we will take you through the challenges of how we get more power in the car, how we will take more hydrogen with us, how we increase our cooling performance, and also how we combine all this and transfer that power into speed. Now, you saw perhaps already on social media that today is about that more power. Last Friday, we revealed the total power of the Forza 9. If you haven't seen it yet, here's the video. So we will be covering more power today. Of course, I won't do this by myself. For that, we have 2 of our fuel cell engineers with us who will be able to explain to you how the system works, what they worked on this year, and also to answer all of your questions that you might have. The 2 engineers that will be joining us today are Munir Rodeburg and Pranav Madhabushi. So guys, if you could join the chat and introduce yourself, that would be very nice.
So thank you, Jesper. Hello, everybody. My name is Munir Rodenburg, and I am one of the 3 fuel cell engineers at Forza. So my main job is actually to design and build the systems that are responsible for giving the fuel cell the best possible air it can actually have.
Hi, everyone. I'm Pranav Marabushi. I'm another fuel cell engineer at Forza this year, and I predominantly work on the hydrogen side of the car. So this involves setting up a system in order to actually provide the hydrogen gas at optimal conditions.
All right, welcome guys. So we just found out how much power the next car will have, 400 kilowatts. But where does please tell us, where does this power actually come from? A hydrogen electric race car, how is it powered?
Right. So in our race cars, we use a fuel cell stack for a steady stream of power. And on top of that, we actually use an electric accumulator. And this accumulator, as you can see from the image, regenerates power during braking, converts kinetic energy into electrical energy, and we can actually use that during accelerating and spend that energy. How does this process work? As the car brakes, we use the electrical motors to generate electricity, like a dynamo. This energy is then transferred and stored in the accumulator. The accumulator is a set of supercapacitors that store and discharge energy rapidly, very much like a battery. However, the accumulator is much faster than a battery. So the accumulator is sort of a shot of adrenaline for the car when it accelerates. It's a slingshot around the corner when we want to really boost our car.
All right, so that's the system in a nutshell. But of course, you're a fuel cell engineer, so I imagine you would like to talk about that. So let's dive a bit more in this so-called fuel cell. We actually had a poll on social media to ask if people knew what a fuel cell was and how it worked. Actually, 1/3 of the respondents didn't know yet. So maybe you could explain what a fuel cell is and how it works to the people.
Perfect. So yeah, a fuel cell is a bit of a difficult matter, but let's zoom in first. So what actually happens inside of the fuel cell? So we actually have hydrogen molecules and oxygen molecules that are actually being recombined. And this recombination of the hydrogen molecules and the oxygen molecules gives us our desired electricity and water as a byproduct. So maybe nice to show how it actually looks like in a fuel cell. We can actually zoom in a small video. So here we have a video of the actual electrochemical reaction, which happens in the fuel cell. So we have hydrogen molecules coming in from the left side, and at the right side, the oxygen molecules are coming in. So the hydrogen molecules are the purple ones, and the oxygen molecules are the blue ones. So in the middle of this video, we actually see a membrane, and at the membrane, the hydrogen molecules are being split up into two protons. And because the hydrogen molecules split up, a so-called electron escapes. But the nice thing of this membrane is actually that the electrons cannot go through the membrane. So they have to follow a different path. And this path is actually the electricity we use in our car. And once the electrons arrive at the other side of the membrane, and also the protons can then be recombined with the oxygen from the air back to water. So now that we know roughly what happens at the membrane in a fuel cell, we can now actually zoom out and look at an actual fuel cell stack. So here we see a picture of an actual fuel cell from our stack supplier Elringklinger. And in the middle, we see a fuel cell. Actually, we see a thin plate of the fuel cell. And this thin plate is actually the same as you saw in the previous video, like the membrane in the previous video. And at the membrane, this thin plate is actually where the hydrogen and oxygen are being recombined to water. So you actually have a lot of thin plates where this reaction occurs. And at both ends of the stack, so in the picture, we see two black plates, and they are so-called bipolar plates. And they are actually very similar to a normal battery, so a plus and a minus pole, because we actually get our electricity from both ends from the stack, from the black plates. However, the black plates, they also have two other functions, which the first one is actually to get the oxygen, the hydrogen, and the cooling water to the membranes. And the second one is actually to hold all the the thin membranes together. And that's roughly how a fuel cell works and how it looks like. So you could actually say that the fuel cell is somewhat of a very big sandwich. The membranes are the slices between the two bread buns, and the bread buns are actually the bipolar plates. And each slice gives the sandwich a bit more flavor, in this case power. And together, all the slices gives us the total power we want. So a big sandwich with a lot of flavor, I would say. Yeah.
So a nice sandwich that produces electricity and water from hydrogen and oxygen from the air.
Exactly. Yeah.
Nice metaphor. So we get a question in chat, which is a question if we use lithium capacitors instead of lithium batteries.
Enough?
Yes. So yes, we do use lithium we use supercapacitors and instead of batteries, mostly because they actually have a much faster discharge rate. So conventional electric vehicles actually use batteries because that's the discharge rate is not really much of a problem. But for us, we really need it as a boost. And the main source of power actually comes from our fuel cell stacks, which is why we use supercapacitors instead of batteries.
Mm-hmm. Okay. Let's see. So, well, you've explained the sandwich. Yeah, the nice metaphor. But in the beginning of our live stream, we showed that the Forza 9 will need twice the amount of power in order to actually reach GT performance and be able to compete. So we need to produce at least that 400 kilowatts with the car. But Manav, you also talked about the accumulator that we have in combination with the fuel cell. How is this actually integrated in the car if you look at the power that the car produces?
Right. So the accumulator actually provides a lot of power, 200 kilowatts of power. But this is a boost. It's very instantaneous and lasts only for a short period of time. So it's only there to give that extra oomph to the car. But to meet our ambitions, which is to actually race in the GT class, we need a more steady and powerful continuous source of power. And this is where our fuel cell stacks come in. The fuel cell stacks will also have to be much more powerful than what we had before. We would need these fuel cell stacks to actually deliver 200 kilowatts of power continuously. Our stacks can go up to 270 kilowatts at peak power, but they really operate around 200 kilowatts continuously. So to put that into context, that's around double of what we currently have in the F8, the existing car that we have, which is a tremendous increase in performance.
Mm-hmm. Okay. So you say your fuel cell has to be much more powerful as well if you need that 200 kilowatts, as it's double of what we have in our latest car. As a viewer, you might think, how do you get more power out of a fuel cell? Do you just make it larger? Do you do any other improvements on a fuel cell? To answer those questions, we actually have Dr. Zahid, who can explain this very well. He's from our partner Elrinklinger, and they produce and develop the fuel cells that we will be using in the next car.
Let me answer the question how Elrinklinger gets more power out of its fuel cell stack. There are two main reasons. The first one, the patented metallic bipolar plate design, which enables an extremely compact sealing concept and an optimal active area usage. The resulting volumetric power density is high and it amounts 5 kilowatt per liter, including end plates. This design can only be manufactured by means of high precision production processes, which have been developed based on series production processes existing at Elrinklinger. The second is the flexibility of the stack to be operated at a high cathode air pressure, up to 2.5 bar absolute.
All right. So I see we also got a question from Monique Roman about what the top speed will be of the new car. For that, actually, you would have to tune in for another live stream in August, which is about the speed. We have another question from Stijn Heitinga. Do you guys also need the double amount of hydrogen on board? That will be in the live stream next month, which is about more hydrogen. And then we also have a live stream in July, and that's about cooling and aerodynamic performance. So if you have any questions on that, be sure to check in on those live streams. What we just saw on the video from Dr. Zahid, that you can improve a fuel cell also with two things. One is improve bipolar plates, and the second thing is optimal usage of the active area at the membranes. Now, these are very nice terms. You guys use them a lot. I don't. I also assume that the people at home don't use those terms daily. So could you maybe explain a bit what these terms are and how that improves a fuel cell?
Yeah, absolutely. So I will go through what the bipolar plates are, and I'll leave the optimal usage area to Munir.
Sure.
So the bipolar plates are essentially surface areas that actually allow hydrogen and oxygen to interact together and in the chemical reaction to produce electricity. Now, these plates are really not smooth. They have grooves on them to actually direct the flow through a flow path for the gas. And you have to really think about these bipolar plates as barbecue grills. You know, if you optimize your barbecue grill, you can grill your food faster, better, or both. Now, the lines on the grill, the metallic lines on the grill, are like the grooves on these bipolar plates. By actually optimizing these grooves, you actually optimize the flow pattern of the hydrogen and oxygen gases and actually expose them to the chemical reaction a lot more. This way, you actually produce electricity more efficiently, and you can get more power out of your fuel cell stack.
Okay. And the optimal usage of the membrane, Munir?
Yeah, so as you mentioned, we do like our terms. That's correct. So one of the other terms is actually optimal active area usage. So it's actually a good thing to remember that the conversion of oxygen and hydrogen occurs at the membrane, which we refer as area in optimal active area usage. So you can actually see that from the rectangle. However, older fuel cells do not actually use all the area of the membranes to convert the hydrogen and oxygen to water and electricity. So the area of the membranes that is actually used is called the active area usage, which is in this case this pink rectangle. And with newer fuel cells, for example, the stack we are going to use, we can actually use more area. So to produce electricity, and that is achieved by optimizing the surface of the membranes. For example, as Pranav just explained with the bipolar plates, the black plates, that you can increase or actually optimize the grooves, so the metallic parts of the grill, so to say.
Mm-hmm.
So that's actually similar for, in this case, for our membranes as well.
Okay. So then you have these two things, and the conclusion was you get to a high volumetric power density.
Yeah.
Another nice term of yours.
Another nice
what
term.
does what is it, and what effect does it have on the system you design?
So yeah, high volumetric power density, again, another nice term. So we can actually compare it best, I think, to an athlete, so to say, because well, an athlete wants to be as strong as possible while being light and as small as possible as well. So if we look, for example, to Usain Bolt, and if he would be as strong as he is right now, and but twice as big or twice as heavy, I don't think he would run the world record in the 9.4 seconds, I think, or well, I'm pretty certain of that. But that's actually similar to our fuel cell. We have a fuel cell which is able to deliver roughly the same amount of power as our current stack, but it's only half the size and half the weight of it. So that is actually quite amazing. And for our new race car, we will be using not only one, but two fuel cells. So because of this high volumetric power density, we can actually place two fuel cells with double the power while only using the same amount of space and weight. So yeah, and that's how we actually reach our goal of providing our fuel cell or our car with 200 kilowatts of continuous power. Yeah, pretty neat.
That's pretty nice. So a logical question would be, why not use two fuel cells, not one big one? Why wouldn't you? For example, I wouldn't see a Formula One car with two power units and all the systems attached to that. Now, there's also Lonke Notenboom, who asked the question if you can keep adding slices to a fuel cell, or if there's a maximum size to this sandwich. Maybe combine those questions.
Well, it's actually a really nice thing. So yeah, there is a limit. Because if we put oxygen and hydrogen at the beginning of the stack, so to say, you would need to have to redirect all the hydrogen and oxygen through all these membranes. And you want to have that your last membrane can actually have as much oxygen and as much hydrogen to get a proper electrochemical reaction. So if you would make your stack bigger and bigger and bigger, at a certain moment, the oxygen and hydrogen could not reach the last membrane, such that you have a proper electrochemical reaction. I hope that answers the question correctly.
And why then not use one but two? Like, are there other advantages, Pranav?
Indeed. So in theory, having one large fuel cell stack seems like a good idea, right? It's quite simple to operate, relatively speaking, of course. But there are many advantages to having two fuel cell stacks. So as Munir actually mentioned, having two fuel cell stacks would make the stacks actually run more efficiently, because when you have one large stack, you end up having cells within the stack that may not operate at the same efficiency as some of the other cells. Right? Having it smaller means you can ensure this higher efficiency. And having one large stack would also mean that it would take more time to increase or decrease power. So the technical term would be to ramp up or ramp down. And this is, of course, a challenge for us when it comes to race conditions. We want to be able to accelerate and decelerate as quick as possible. So another advantage of having two fuel cell stacks is actually it allows us to place them independently and separately in the car. And by doing this, it allows us to fit our components around them in a way we would like, instead of it all being clumped together. And finally, actually, we can operate both stacks independently. By doing this, you don't actually limit the condition of one fuel cell stack to the other, as they're operated completely separately. And this makes our car more reliable during the race.
Okay. Thank you. I see we have another question from George van Hof, and he asked, how heavy is the fuel cell stack?
The fuel cell stack actually weighs around 43 kilograms per piece.
Okay. And then, so we have the system now, two fuel cell stacks, two fuel cell systems. This power they deliver, this 200 kilowatt continuous power. Does that all just immediately go to the wheels, or do you have losses in the car? Like how does that work?
Yeah, so that's a good question. So indeed, we do generate a lot of power, but not all the power the fuel cell generates is actually going to the wheels. The power that is actually being used for other systems is actually called parasitic power, and we don't like parasitic power at all, and we want to be it as small as possible, actually.
Okay, but what is this parasitic power exactly?
So parasitic power is, as I mentioned, the fuel cell gives not all its power to the wheels, but it has a part of which it has to give to other systems, because the fuel cell itself cannot operate on its own. It needs systems, for example, that deliver the air, the hydrogen and the cooling water to actually make your fuel cell operate. So, and these systems, they require power on themselves. And well, yeah, that's what we actually use for to operate our fuel cell, and that's what we call parasitic power. So actually a nice example, I would say, for parasitic power is the compressor. So here we actually have a picture of a combination of a compressor and turbine. I will come back to that later, the turbine. So don't mind the smaller text, just follow the colored arrows. Those are the most important ones. So we use a compressor actually to get our air into the fuel cell, so the oxygen, which is one of the key components in our reaction. And the air gets actually into the compressor following the blue line, the blue arrow. And the air is then being compressed within the housing, the compressor housing, and the air leaves the compressor with a higher density, and that goes towards the fuel cell. And this higher density actually has another benefit, which actually increases the power efficiency of our fuel cell. So it is actually a double win. We get our air towards our fuel cell, but we also increase our efficiency, and therefore actually the power. However, as I mentioned before, the compressor uses energy to compress the air. So with the new car, we are actually going to use a turbine as well. And with the turbine, we can get some of the energy we used from the compressor back. So here we actually have another picture, which is our new compressor of Fischer, which actually is a very neatly integrated compressor. And we actually received this one last week, so we are happy to implement it in the new car.
Nice to see finally.
Yeah, right. It's really neat. It's really slick. However, to give actually a better example of how our compressor and turbine works, we should better go back to the previous drawing. So you could say, well, think it of in this way. We actually have air, and the air is actually a spring. And when we put the spring, so to say, inside of the compressor, the spring is being cramped down. So it's going to be a lot of tension on the spring. And the spring is then actually going, for example, through the system. And at the end, the spring is getting back into the turbine. So the red arrow there, it's entering. And the turbine, what it actually does, it decompresses the spring. So the spring becomes larger, and all those forces which are being released are the forces which we can directly use for the compressor again to compress our air. So the demand of the electric motor, so the parasitic power, is actually being less this way. And this is one of the ways, or many ways actually, how we try to decrease our parasitic power as much as possible. And because after all, we are building a race car, so we have to improve on any kind of aspect to minimize our parasitic powers.
So basically the outgoing air spins the turbine, and that helps to spin the compressor for the incoming air.
Exactly. Yeah.
Okay.
Correct.
So it's not just one fuel cell, or it's not just a fuel cell and magic, and you get power out of that. You need all these components that help to operate it.
You need a lot of components. Yeah.
I think it gives a very nice picture of your job this year. It's not just only, of course, designing these systems around it, but also making sure that it's most efficient, and that you try to win back energy or lose as little energy as possible, so that as much as possible can go actually on the road.
Exactly.
Indeed,
Yeah.
yes.
All right. We have another question from Nikola Ninkovic, and he asked what the voltage range of the fuel cell is, and if it's also connected to a boost converter.
So with respect to the voltage range, if I have the numbers correctly on top of my head, like when there's no current being drawn from the fuel cell, so it's open circuit voltage, it's around 570 volts, if I remember correctly. Um, Regarding the boost converter, um, um, I'm not fully aware of that. I don't think we actually use a boost converter because I'm not, well, there's my colleague from Electro, but too bad he's not here to back me up. So I actually do not know. No, sorry.
I mean, we do use a DC converter, of
That's
course.
true. Yeah, yeah.
We have another question from Stijn Huytinga. Does the air need to be cooled down before it enters the fuel cell stack?
Yeah, it actually needs to be cooled down. So we actually use a intercooler after the compressor because first of all, before the air is actually entering your fuel cell, it needs to be humidified because the fuel cell doesn't want to be completely dry.
So you need to add water to the air.
Yeah, exactly. You need to add water to your dry air. So, but the humidifier cannot operate at very high temperatures, nor can the fuel cell. So yeah, we have to cool it down, and we cool it down to roughly 80 degrees Celsius.
Mm-hmm. Okay. We have some other questions as well from the social media. People sent in. There is a question if we build our own fuel cell.
No, we don't. No, we do not. I think
wouldn't you like to build it yourself enough?
Yeah, I don't know about that. I mean, the complexity involved is like starting another dream team and a company of its own. That's the companies that actually produce this are, you know, massive OEMs that are, you know, billion-dollar companies. I think it's not worth our time to actually go into that. You know, so I think it's best if we actually look at how we can make the car as a whole better rather than an individual component.
Yeah, I think also to add on that is that we last had a lecture from Siemens where we could how to design a fuel cell. Well, I then saw the complexity to like on a molecular level how things should be designed to optimize the fuel cell itself. Well, as Pranav mentioned, I think you can start your own dream team again if you want to design your own fuel cell. But yeah, so we will leave the task to our partners, ElringKlinger. Yeah.
All right. So there's also a question about which catalyst we use at the cathode and anode of our stack. Is it a question we can answer, or is it a question we would have to forward them to our partner, ElringKlinger, for that?
Well, I'm not fully aware of what exact catalyst they use, but normally they use platinum, but there might be a smart trick right now regarding the type of catalyst. So I think the question can be best redirected to ElringKlinger, just to be certain. Yeah.
All right. And let's see. Yeah, okay, I see more questions about top speed, about downforce and drag reduction. Those are, of course, for the other live streams. There are also some more technical questions. Maybe you could explain a bit in easier terms as well. One question, for example, is if we use an exchange medium, like what kind of exchange medium we use for our fuel cell.
Yeah, so if I understand the question correctly, like the exchange medium, so I suspect that it's the membrane inside of the fuel cell. So we spoke about it that it can only let protons go through the membrane. So if we actually zoom, well, before I zoom in, the name of the compound which is used normally as the membrane is called naphthalene, but there are many small deviations on the compound naphthalene. So I don't know if it's the material naphthalene itself is actually being used, but the general way of naphthalene is actually it's a very long structure of carbon atoms in the form of a branch structure, And at the end of the branches, like normal branches have leaves on them, but in this case we have so-called fluor atoms. And you could actually layer these fluor or these branches, and you get like a woven structure of these branches. And if you have those fluor atoms, they could form pockets, and those pockets are actually small gateways for the protons to actually go through the membrane. So that's what we actually use as a form of a transfer medium. Yeah.
Okay, so these pockets actually make sure or make the fuel cell work in that the protons can go through, but not the full hydrogen.
No, well, not the electrons could not go through. Yeah, exactly. Yeah.
Okay. We have another question. Also still technical, but a bit easier to explain. It's of course you've studied chemical engineering, so the last question was right up your alley. But the question is, we have shown that we have these two fuel cells, and the question is, why is our car not? Why wouldn't it be twice as large as our latest car?
Yeah, so in our new car, we take actually several steps to make sure this doesn't happen, because this would be catastrophic to our race. So we actually fit the components in a more organized and structured manner than that we have done in previous generations of the Forza cars. And we do this by using CAD software or computer-aided design software to actually place the components in a virtual car that we built. This way we can see how well the space is utilized, how much more space is available actually, and what potential pitfalls we can see in the future when it comes to packaging the entire system together. Now, another way that we've actually prevented the car from just expanding is by using newer technology. As you can imagine, hydrogen technology over the last few years has become a booming industry, right? As we have seen in the Tokyo Olympics, everything is becoming more hydrogen oriented. And because of that, there have been a lot of technological advancements in not just hydrogen cars, but even the components for these cars. So as an example, we have seen the fuel cell stacks that we spoke of before. Now we're able to get fuel cell stacks that are the same power for half the weight and half the volume. This is an incredible achievement. And so many components like this are becoming more and more available on the market for us to also acquire or design around. And but also inherently, doubling the power of anything is not necessarily a linearly related to the size of the car. If you have a Toyota Corolla and a Bugatti Veyron, their power differences are very different, but their sizes aren't linearly extrapolated, right? So it's not always directly correlated.
It's not a truck.
Indeed.
Okay, we have time for one last question. And when we're speaking at events, we also get asked these things a lot. Of course, we're working with hydrogen. Many questions go towards safety. People ask many questions on events, like, what does this mean for us? What is it like driving a hydrogen car? Is it actually sustainable? How far can you drive? Like, is refilling really that quick? But also about safety. And the question is, if it's not dangerous to produce so much power in that one car.
Yeah. So I'm one of the safety officers of Forza, and one thing that is crucial in our designs is obviously the safety. And well, we design our systems so in a way that each system can be able to handle our desired powers. So next to that, we also put a large safety factor on it. For example, the devices are able to easily hold twice the power output before actually anything goes wrong. However, as I mentioned, the systems, they are actually not being able to reach those powers. So I would say our systems are rather safe to handle these powers. Yeah.
Okay. Well, that was our last question we have time to answer. Not all questions have been answered yet, but those will be answered personally. Also, if you have any questions you still would like to ask, please do in the comments or on social media. We will make sure to answer them. Thank you very much, Meneer and Pranav,
Yeah, you're welcome.
Yeah.
for being
Thanks for
here,
having us.
for your explanations, and especially your nice metaphors. Also, I would like to thank Dr. Zahid of Elrinklinger for the information and the material that we could use for this live stream. Thank you for joining in, of course. As a viewer, next month the topic is about more hydrogen, because we have more than twice the power compared to a latest race car. Does it also mean we would have to bring more than twice the amount of hydrogen? Find out next month if this is true. Get to see more pieces of the puzzle of the Forza 9, the next generation hydrogen electric race car. But before I will say goodbye, I would also like to thank Daphne, Anna, and Seymour. They're working behind the screens to make everything right. Hello,
There she
Daphne.
is.
Also, Anna has been forwarding all the questions. It's her birthday today, so
Happy birthday.
show some congratulations. And yeah,
Getting old.
we'll see you in the next live stream. More hydrogen. Also, again, more about what does this mean for me? How far can we drive actually if I would have my own personal car with that amount of hydrogen? How far can I go? Things like that. More interesting reveals about the car. So see you then. Thank you.
Bye-bye.